Oh, okay. So today it's not so difficult lecture and really cool lecture. So as usual, like half of the lecture, I say it's my favorite lecture. So this one uh, I really like. So we will speak about AdaBoost algorithm. And so it's so there was a theoretical questions about cryptography in 1989, 35 years ago, and students could not solve it. But the algorithm they have to find is really easy. It's solved by non-adaptive boosting. And so I will present the algorithm. And so the idea is as follows. So imagine that you want to build spam filter for email. So you want to classify emails as like real emails and like scam. And so you can like easily invent a rule that works a bit better than random guessing according to the proportions. So, for example, if you see win lottery or uh, get inheritance or oh, time to wake up. Yeah. So if you see such typical sentences, then you can a bit better than random guessing say that this is a scam email or spam email. And so the question is, imagine that you can, for a given training set, you can always come up with a rule that's a little bit better than random guessing. Can you transfer the rule to a rule that's like almost perfect? And so this was a question for crypto. So if you can guess password, each bit of a password with a little bit better than random guessing, can you create a method to guess the password completely? And so answer is yes, but the students did not solve the question. So it was MIT, so a crypto class by a famous professor. But then 2, 3 years later, some people wrote a very complicated boosting algorithm that solved the question. And then in 1994 or 95, so like 6 years after the assignment or 5 years, people found this simple non-adaptive boosting algorithm. Okay, so what is the idea? So let's make some simple example. Maybe you already learned about in machine learning class about boosting. Yeah, so you know. So the idea is that you have a training set and you want to build a linear combination of classifiers. We will take majority vote. We will generate a few classifiers and take majority vote in the end. And the idea is that we have a training set with some minuses. Let's say we have some pluses here and here, but also some minuses here. And the idea is that we start from simple classifiers, say straight vertical or straight horizontal line. So half spaces, but x is aligned. So either vertical line or or a horizontal line. And we also maintain, so algorithm does two things, select classifier and also update weights on the training set. So every point will have a weight. And so initially all the weights of all the points are the same. And we take a classifier, we select classifier with minimal empirical error. For example, we could start with classifier that classifies according to this line. Oh, that's not optimal. We should let me add some pluses here so that it's optimal. So here we have some line. And the first classifier will say minus here and plus here. So this is our first one. And then we update after selecting classifiers, we increase the weight of wrongly classified points and decrease the weight of correctly classified. And then we again select a classifier that does better than random guessing, but relative to the new weights. So let me say how it happens. So the points, so these three are correct. but these 4 are wrongly classified. So the correct ones gets a smaller weight, but then the wrong ones, I give them bigger weight. So I draw them by drawing them bigger. And then the other ones, they have a smaller weight. So these are the new weights. Now we select a new classifier. But now these minuses are pretty important. So the new classifier might something like this. That's our new classifier. It selects plus here and minus here. And so now these points are wrongly classified. So we decrease the weights of all other ones, but increase the weights of these ones. So we get the third classifier. First, let's update the weights. So these ones get a bit bigger. These pluses were already very small, so that they become really small. Then here we have, we should put the line a little bit lower. I will move this plus a little bit up. Little plus. And then these minuses becomes a bit smaller. This minuses becomes really small. But here the pluses are a bit bigger. These two pluses become a bit bigger again. And now we take a classifier according to this weight. So all these minuses are important, these pluses are important. So the third classifier will be something like this. Okay, I will go, maybe this plus is, okay. You got the system like this. And so now we have 3 classifiers, this one, and this one. And we combine them by taking majority vote. So it's visible with the camera because in Zoom, it looks pretty good. So, and I have some extra space here. So now we take majority vote. And so we have here. So our majority vote looks something like this. So here we have plus, minus, and then we have minus plus, and here we have plus minus. And now let's insert the points. There are 2 minuses here, minus, minus, pluses here on the line. 2 pluses. There's some more pluses. These are pluses are on. Okay, just an example. Like this. And so we see that now there are very few, the majority vote makes a few mistakes. So let us check. So here we have minus from these 2. So we have 2 correct classifiers. So these in the middle are okay. These are also okay. Here we have 2 pluses. So this is also okay. This is also okay. Here we have 2 minuses. These 2 are also okay. So our classifier that takes majority vote is right everywhere. So that's the boosting algorithm. So let me now write down the algorithm. So it's called non-adaptive boosting. And what we have is 4 things are the input, a set of base classifiers, a training set, parameter A, and a number of boosting rounds. A will be number between 0 and 1 and controls the scaling. So set base classifiers. And so we will use A equal to -1 plus 1. So then the second thing was trainings. Let's first do the parameters. So there is A, and A is strictly smaller than 1 and strictly between 0 and 1. There is a T is number of boosting rounds. And finally, there is a training set. Before already been using the training set. And so algorithm. So we initialize, there are the weights. In the first round, first input, they all have weight 1. So all elements in the training set have weight 1. So non-adaptive boosting, so make small error on the training set. And then we start the main loop, and there are only 2 instructions: select best classifier and update the weights. And then we output majority vote. So let's write it. So for t equal to 1 till t, and then we set, so we say that ht is classifier with minimal weight of 1 of minimal weight wi. Okay, I need to write better so that it's readable. But I can write those here. Right. Wi. So we iterate over all the training points, and we sum up the weight of wrongly classified points, and we minimize this weight. And so then the second is update of weight. So for all I smaller than n, we say that w t plus 1 equal to a to the power yi I times w. So we multiply by a to the power yiht of xi. So here I use that the labels are, the idea is that labels are -1 plus 1. So if classification of ht is correct of point xi, then the weight decreases because a is smaller than 1. Is it readable? Yes. And so the weight is smaller than 1a, so weight decreases. If the prediction of ht is incorrect, then we have a to the power -1, so the weight increases. It's very familiar from from online learning, but now it's kind of different because the weights are not on the classifiers in the training set, but the weights are on the training point. So by the way, the person who invented this was from online learning, was studying online learning. So it's natural to do, but then he had this idea. And then the output is a classifier that maps x to the sign of h1 of x plus h. So that's non-adaptive boosting. This is very simple. So just two rules in each round. And so pretty easy to remember. Yeah. Probably write such a line to be nice. Okay. Yes, and now there is a nice theorem that says that empirical risk decreases exponentially fast in the number of boosting rounds. If we can indeed find, if all classifiers do indeed better than random guessing. So let us use some notation. So, let us have a small definition. I will write it here. So let us say that probability when we take I from WT is the natural thing, right? So we have a weight vector. So probability of probability HXI not equal to YI. So it is equal to the sum divided by sum over all WI smaller than n, and here we have sum of WI HXI not equal to, I still have some extra space. But we already use it in online learning, this notation. And so we say that if in each round probability of HT xi for I from WT is different from YI, if this probability is smaller than 1/2 minus gamma, so if we are successful, then we have that empirical risk on training set S of Fs. So this is the output classifier Fs. Is smaller than exponent minus 2 gamma squared T. So this is really cool theorem. It says that empirical risk decreases exponentially fast in number of boosting rounds. So if this is true for certain gamma, then how many rounds do you need? Well, you need ln n divided by 1 over gamma squared rounds. So if gamma squared is like whatever 1% or something, so you do just 1% better than random guessing, oh, that's still a lot. And then you need 100,000 boosting rounds. Okay, if gamma is 10%, then it's 100,000 boosting. Okay, but this is just theoretical upper bound. So in practice, it can go faster. And so let us prove this theorem. First observation, let us bound the 0-1 loss. So this is based empirical risk on 0-1 loss. So let us say that, some simple observation, HT of X. Okay, let us first use some function. So let us write G to be the sum. G of X is equal to H1 of X plus HT of X. And now let us look to G of X times Y. So indicator of this being bounded by 0. So this is an upper bound on the 0-1 loss. So it might be slightly more than 0-1 loss in case G is equal to 0. Because of sign function, okay, just a detail. So this is upper bound on 0-1 loss. And we know that this is bounded by a to the power gx of y. So why is it? Because a is smaller than 0. So if this is positive, then it's trivial because this power cannot be negative. But if but g of y is smaller than 0, so this is real valued function. So before taking this out, but when g is smaller than 0, product is smaller than 0, then we get something bigger than 1 because a is bounded by 1. So this is true, and so this is equal to product of a of ht of x times y. And so if we insert ith element here, and so this just by definition of G, so this is very easy. So it's going to be easy lecture today. I mean, there is a lot of material, but not so difficult. So so we have this product, and so do you know what is this product? We can write it even easier. So look to the algorithm. So to what is this equal? Yeah. So, but I need to take the product over the t. T equal 1 to big T. I've made a mistake. So this is precisely the weight after t rounds. So in the last round, we have some weights and we don't use them. And these weights appear in our precisely equal to w t plus 1 comma I. So this is precisely equal to this. So now you might have some ideas how we will get to the proof. And so we want to bound empirical risk. So we need to take the sum over this and divide by n. So we will be basically looking to the sum over all the weights, like we did in online learning. Nothing new. So the empirical risk R over Rs of generated classifier. Actually, I don't need this Fs, but I can write sine of G. I have fewer symbols, doesn't matter. So it is bounded by sum of W t plus 1 I smaller than n divided by sum I smaller than n of W1I. And here I'm using that all the initial weights are equal to 1. So this sum is just n. And so empirical risk has factor 1 over n in the definition. And sum of number of mistakes divided by n. And so here, this is bounded by the sum of mistakes, and this is equal to n. And now we know what is our next step. So we do the same thing as in online learning. We will look at each round how the sum of weights changes. So now our task is to look at sum of W t plus 1 comma I divided by sum of W t comma I. Oh, I smaller than n. I smaller than n. Okay, and so there are two, so we have to look at updates of weights. There are two types of updates. Some weights increase and some weights decrease. So we will have two sums. Let's first look at weights that increase. And so that's where, so the sum over all I, where classifier is wrong. So hxi not equal to yi. And so we have here, they become a factor a bigger. Okay, so maybe I can just write it directly. So I will have H2 probability that ht of xi not equal to yi plus a to the minus 1 times probability that they are equal. HT xi equal to y. Okay, so I'm writing in the middle of this definition, but that's precisely the moment where we need it. So is it clear? So do I need to write what's in the middle here? I don't, sorry, should ask one question. So is it clear? Let me write. Yeah, okay, very cool. And so just because I'm kind of lucky or unlucky that the definition is right there. And this is really cool. And now that is, yeah, we'll remove something from beginning of the not needed anymore. So our task is just to bound this by something. And so here for each round we have this expression, and we know that this probability is small. And this is 1 minus this probability. And so let us write it again. So this is exactly equal to A times probability, let's say error, HT error, plus 1 over A, 1 minus probability of HT error. Okay, and so now the bigger is this. So we want to prove that this is, we want to prove upper bound this. And so we want to prove that this is lower than something. And so to make it as big as possible, we should make this error as small as possible. Sorry, that's not what I want. So I want to bound that this is, we want to think. Okay, something happened. And so when we make, oh, I made a mistake here. When we make an error, we increase the weights. So here we should have -1, and here we should have +1. Okay, now it's right. And so when we are correct, we multiply by A. A is smaller than 1. So we have here 1 over A, and here we have A. Okay, and so now we want this error to be maximal to get an upper bound. Okay, so if this error is very big, what's happening here?
I think it's evident from the derivative. So the derivative is 1 over A minus A, so it's bigger than 0. So we take the maximal value for probability of each t makes a mistake.
Yeah, so this is big. Yeah, the bigger is the probability, the bigger is this value. And then we plug in the upper by people already understood. So this is bounded by 1 over A, 1/2 minus epsilon plus A times 1/2 plus gamma, sorry, epsilon. Okay. Oh, and I forgot to tell which value of A we need to use in the theorem, which is kind of if this, and so we will use the best possible value for A according to this inequality. And so we need to pick A precisely for this result. And so which is the correct one, the one that optimizes here. And you know how to optimize, because it happens like already a huge number of times in the course. We take the square root of the two factors here, about the square root of ratio. And so we have 1/2 minus gamma divided by 1/2 plus gamma. And so this is indeed smaller than 1. If gamma is positive, of course, gamma is positive. So for this value, we will have that this is equal to 2 times square root of 1/2 minus gamma, 1/2 plus gamma. And so now we do some advanced mathematics. This is bounded by 1 minus 4 gamma squared. And this is bounded by exponent minus 2 times 1/2 because of the square root times 4 gamma squared. So this step, okay. And so 1 minus 4 gamma squared bounded by exponent minus 4 gamma squared. But then there is a square root, so we take, so we take square root on both. Clear. Voila. So this theorem is proven. Yes. Okay, but this algorithm is not optimal because we need to tune A, and A could be like optimized in the proof here. And so remember, I was struggling actually here. I was saying, oh, that's what is this error here? So when we select base classifier, we do know the minimal error. And so why not optimize A directly in the proof here? And nothing goes wrong. We can just do it. And so this is AdaBoost, the adaptive variant of the first boosting algorithm. And so, so what changes in the algorithm is that here in the middle we have 2 extra steps. So first we don't need this A here, and then we will have AT computed here, and I need to write it somewhere. So let us. Okay, this is important equality, but I can. Let me rewrite everything. So let us first. And so if you really understand the proof, you might guess what is AT. So first we compute the error. Epsilon t is equal to probability I from WT that HT of xi not equal to yi. And now we tell the weight AT. And so what should AT be? Just by analogy. So here I used this thing. So what should AT be? Well, 1 minus gamma is upper bound on error. So we set it equal to the gamma, to epsilon t. And here we have opposite. So here we have the error epsilon t, 1 minus epsilon t. And then we choose A that optimizes, that minimizes this bound. This is very important. And so idea is we minimize this bound. Why do I say it's very important? Okay, I will explain myself later. I still need to say what is the, okay, now, if you really understand the proof, you can also tell what is the output classifier. Well, first I need to say what's the updated weight. But nothing changes, we just use AT instead of the fixed A. Yi. So t plus 1 I goes to yi h of xi. And now we need to say what is output classifier. And this, if you understand the proof really well, you could already tell what is output. X maps to oh. Oh yeah, but it's a bit difficult. I erased the definition of G to understand what it is. Well, what we were using is bound of a single weight in terms of the G function. So now what is WT plus 1 times I? it is equal to, so it is product over T smaller than number of boosting rounds of Y HE of X. And so this is our new expression for the weight. We start at 1 again. So when we build our upper bound, we will have a function G, but now we take a weighted majority vote. So that's the difference. So if our bound here is very good, then the optimal value for A, so if our error that we get here is really small, then the optimal value will give us a very small A, so that this weight is very big. So to get minimum upper bound. And that means that here in our weight, this A has a huge term. And let me just write it because it's a bit difficult. So H1 of X times ln 1 over A1 plus, and then we take the sum over all the way, over all the classifiers. And I forgot the sign function. Output X maps to sine of was HE X ln 1 over 18. That's the output.
Can we just explain that how to get the
Yeah. So you take the logarithm with any basis. It does not important which basis, because it's just a linear scaling under the sign. And what's the idea? How to get it? So here we define a function g, and the function g has to come in the exponent. So we could say that this is equal to exponent of yi g of x. What we did before. But g of x is precisely what is inside the sign. And so then the same proof precisely goes through. I will skip the calculation. Because we just updated the weight, so now all the weights depend on t, but we at this point we only work with g function in the proof. So everything continues. And so you got the bound for AdaBoost. And you already learned that so in AdaBoost. And so then we have precisely the same theorem. And this theorem was in machine learning course already. Okay. Yeah, I don't know. So there was like a few years, around 2010, 2012, AdaBoost really simple, and it was better than. It was competitive with neural nets. It's incredible, such theorem, such a few rules, easy to. So they implemented. So base classifier were decision trees with very small depth, and sometimes even decision stamp. So just checking one coordinate threshold on one coordinate. But then a few years later, neural net came, and they are the winners since for more than 10 years already. So although when I came here, I was teaching to some theoretical computer science to some people from Yandex, and I asked, "What's your favorite classifier?" It was 2015, and they say gradient boosting. So yeah, no, it's 2017. Yeah. Okay, so now we understand the basic theorem. And what will happen in the seminar? So people understood that it was useful in practice, that like they slowly, this 1994, 1995, they understand that it's nice algorithm, but then it took like 4 more years before it starts to really win something. So it depends on available computation power and data sets and so on. And then it became popular. But then people realized that actually this algorithm was one of the oldest machine learning algorithms. So there is a no, not really machine learning, but there is old optimization algorithm called coordinate descent. And this is just coordinate descent. It was known algorithm where we just optimize this bound on the loss function. And so here is some. So here we have that G is convex linear combination of base classifiers. And so here is an upper bound on the empirical risk. If you apply this algorithm coordinate descent on this upper bound, you get precisely AdaBoost. And then the people say, oh, okay, but then I can change this upper bound. I can invent a special upper bound for multi-class classification, or in the seminar, there will be boosting with abstention. I forgot the word. So there the boosting, so it's classification like 0, 1, but boosting algorithm can also say, I don't answer because I don't have clear. So my majority vote is close to this. So we have something close to 0. I don't feel safe to answer. So there is kind of third option. It's like multi-class classification with some special loss function. So you can change it, and then you get a new boosting algorithm just by applying this gradient descent algorithm. So now I will say what is gradient descent, and then we will check the calculations. So it's the next topic. Then we will speak about risk bounds for boosting. So coordinate descent. We have some objective L. So some of the equations I will still need. So here we have the vector alpha. Let's use a different letter M. And so this is our objective function. So we have some convex differentiable function. No, just differentiable function. And coordinate descent will find values that reach local minimum of this function L. And it does as follows. It will first select the coordinate that has the biggest negative derivative, like the lowest derivative, which usually is negative. And then it will find the update only this single coordinate to the optimal value. So it will like do whatever line search or whatever on a single coordinate. So the rule is so for until some termination condition is satisfied. Okay, so let's just say for T rounds, because AdaBoost we also take T rounds. Select S such that the partial derivative E alpha S is smallest. Okay, I guess the natural way is to take absolute value and look to the biggest derivative, because you could increase or decrease coordinate, and then select eta such that alpha 1 alpha S plus eta alpha M is minimal. So, and then repeat. And so eventually you find some new alphas that are optimal. and then alpha goes to alpha s plus eta, and then repeat. Okay, and now the claim is that the gradient descent is doing precisely the same thing. So what are the coefficients in this analogy? So here we consider the base classifiers B. We set them equal to, so we assume the set of base classifiers is finite. It's just let's call them F1 till Fn. And so AdaBoost takes the sign of some linear combination of base classifiers. And so the same linear combination of coordinate, we will get the same linear combination of coordinate descent. So what is L when we make the analogy? So I'll just the exponent, sorry, is sum over the training points of this upper bound on the loss. So sorry, there is a sum missing here, but I will write it now. Exponent yi and then alpha 1 f1 of xi plus alpha n Fm x. So this is objective function, and this is the upper bound on the empirical risk that we were using. Well, okay, n times. Okay, so this is upper bound on n times empirical risk that we were using. Okay, and so now let us look to the first rule. So let us by induction prove that AdaBoost selects the same functions ht in each round and the same coefficient. So here are the coefficients. This is the first coefficient for h1 and so on. So it will update to the same coefficient. So first task, let's look to a derivative. And so which function will give us the biggest derivative? And so which coefficient will give us the biggest derivative? So yeah, then we need to compute derivative. So let's look to dl d alpha j. So it is equal to, so when we take derivative to alpha j, what comes in front is fj. Is equal to sum a smaller than n of yj, no, yi, fj of xi. And then what comes here is this exponent. But note that this exponent is precisely the way to get from AdaBoost. So I can simplify it. So, so if we believe that by induction alpha j is equal to ln 1 over ij. So for j go or let's use c. And so if we believe that we selected the same functions here and we selected the same values so far, let's check that in the next round we use the same values. And so then we can write that in round t this exponent is precisely the same value. Because in the alphas we have logarithms and then we take the exponent, so the logarithms cancel and we have what we need. So so our inductive assumption says that this exponent is equal to wi. And so when we take the derivative, we get the same coefficient, just this comes in the front. And so this is also equal to equal to so there are two contributions. This is equal to 1 and this is equal to -1. So when it's equal to 1 to -1, that's precisely the error probability. So here we have epsilon. So let's first look to those cases equal to -1. It's epsilon ti times the weight of wrongly predicted or the total weight. So sum of WTI over all I. And just probability that you're wrong times the total weight. That's for when it's wrong. And when it's correct, we have something else. I do have, and I need it. And then we have probability that we are right. Again, by summed by the total weight. It's small. Okay, this is bad. Use 2 times the index. Sorry, I don't mean I don't think it like this. I can use I. Okay. So what we see here, it is, oh, in other words, it's equal to 1 minus 2 epsilon t sum of weights. Okay, so which one will have the smallest derivative? That is, oh, little problem. Yeah, so smallest derivative will be, oh.
So the question is, shouldn't there be a minus
Yeah.
before?
Good point. Here we have a minus, and then, so when we are wrong, no, you have exponent of g, there is no minus here.
No, before the epsilon t. So I wanted to say about this. So you just you have just written it right now. So minus before epsilon t. So it's okay now.
Yeah, now it's okay. And so let me check my notes because I said the smallest derivative. But here I have a different sign. Oh, but I'm using another sign for G. So there is in the notes, there is somewhere I made a sign mistake. Because I have extra. I found it. This is ridiculous that I make everywhere this mistake, the selection on the sign of G. No, you know, that's the same. Oh, we are wrong. No. So for some reason, I took the objective with a minus sign. And now I'm confused about the logic of this. Because it's no longer the same as the output here. As exponent of. So, but we need that, this is upper bound on the 0,1 loss. So, but then I took positive connection with, what did I say from the inductive assumption? That's, Where is my conduct after deep boosting round? That's the sign of alpha times B, same. Now that is applies W E equal to. Oh, okay. So no problem. We can just, I think there is a mistake in the lecture notes and somehow it get undetected after several years of teaching. But let's just take the largest derivative and then everything is okay. So then we want the smallest coordinate and yeah, so we want the smallest coordinate and then so this will be precisely the same function. And so which function, so which index S will coordinate this and choose is the one that corresponds to coefficient of base function that makes smallest weight of mistakes. And so it's precisely the same. And if there are ties, we need to assume the ties are broken in the same way. And so same coordinate selected here corresponds to best classifier here. And now let us check the update. So what is the value of eta that will optimize this? So what's the value of eta that will minimize our objective? Here is the objective. So for this, we set again the derivative equal to 0. The derivative we already computed. Here we have derivative. But now we have inside our objective, what is the change in the objective? We have a function eta plus fs of xi. Right? And then in the front there is yi. So when we optimize eta, we compute precisely the same objective, but we fiddle with this eta here. So we have extra term eta here. So when we take the derivative to eta, we have the same derivative with the same thing in the front here, except there is additional factor exponent of eta times fsxi eta I. So what we have here is this thing times this exponent. And because everything is in the weight, just we have this extra thing here, we need to compute eta. So let me rewrite this more clearly. So what we had before. I will just rewrite it. It's a bit boring for the weight. So so we have epsilon t times sum of v I smaller than n plus this is what we had here sum w I smaller than n. And so now we have precisely the same derivative with this extra term inside the exponent, which is extra factor. So we have here e to the power eta times yi fsxi. And here the same, e to the power eta yi fxi. But here we make a mistake. So this is equal to -1. So we have minus eta here. And here we have eta equal to +1. So this is a constant, it's irrelevant for optimization. So when we set delta alpha j equal to 0, this only happens when we set this sum. So we can forget about the sum. So we have eta to the power minus plus e to the power eta.
and again minus before epsilon t. So minus epsilon t e to the minus epsilon.
So sorry, this minus is not here. When we take derivative to eta, yes, you're right. Thank you. And it's very important for that you corrected, because so we have to set this equal to 0. And so we have the same the same thing here. So, well, I actually I should not have taken the derivative. We can see it right away that we have the same weights, just with these two factors here appearing, which correspond to the same optimization problem we have here. So there is epsilon t here, and the weights factor all out. And so this finishes the proof that in AdaBoost, we select the same classifier, and then we update to the same coefficient. And so in the eta, in the S round, will be precisely the logarithm of AS. Logarithm of 1 over AS. Okay. So yeah, it's on the first attempt, this is quite a lot, like on the small board, it's not so easy to explain. But it's carefully written in the note, except for the minus sign. I will correct it after the lecture. Yeah. But yeah, so I already said that we have to look to the absolute value, in fact. So when I say smallest or largest, it's more or less the same thing. Okay. Yes. And now we come to the risk bounds, which is really cool story. So yes, implementation I already discussed. So we can make risk bound using VC theory. So when we have more boosting rounds, we built a very complex classifier. And so we can try to make a risk bound for AdaBoost. And so what is so we can try to use VC theory to find optimal number of boosting rounds. And so let's write down the risk bound. Okay, I remember. So in VC theory we have, so FS is learned classifier. So the risk is bounded by empirical risk of FS plus square root, and then we have here something like 2k over n. K is VC dimension, Ln of and so then we have something in the opposite, Ln over k with some constant. Okay, I don't remember. Let's say 10. It should be enough. Okay, it's not so important. And then we have that's the version from Rademacher bound, 1 over 2n Ln 1 over delta for fluctuation term. So this is always the same. And so after T boosting rounds, you can prove that VC dimension of linear combinations is at least. So okay, so the upper bound is T times K Ln T. And lower bound depends on the base classifiers. Sorry, there's 2 times K. So if VC of B equals B. So upper bound goes up, and if we take decision stumps, then there is a lower bound. So if set of decision stump has VC dimension D, then K goes up by this. And so what we have is a bias variance trade-off on number of boosting rounds. And so there will be a nice minimum. And when K increases, then number of, so after T boosting rounds, we will have a classifier that depends on T, it will go down, and this will go up basically by square root of T, precisely as we had in online learning in the beginning. we also had a mistake bound. And so there is similar bound. And so people tried to run boosting. So one of the first boosting papers, and they had a logarithmic score in the number of boosting rounds. So 2, 3, 4, and then there is 10 and 100 and 1,000, and the graph is in the picture. And I noticed that error went to 0 at, for example, the fourth round. The test error went to 0. Sorry, the train error went to 0. The test error went down to 0 like this. So it's not at all a complexity trade-off. So this is in the famous experiment. In practice, after a huge number of bounds, the error goes like a little bit of the test error. And so how is this possible? And so VC dimension is not good explanation. However, there exists also a bound with Rademacher complexity. And this bound does not depend on the number of boosting rounds. And this has to do with, so that is right, it's because the Rademacher complexity is closed under convex combinations. That's the main idea. So here we take a linear combination of coefficients, and if all the epsilons are smaller than 1/2, then all these coefficients, they are non-negative. So we take convex combination. So this is supposed to happen. But by the way, epsilon cannot be 0. If epsilon is 0, then it will be detected in the first round, and boosting terminates immediately and outputs the base classifier that makes 0 error. This kind of trivial case, I skipped it everywhere. Okay, so risk bound with VC dimension, with Rademacher complexity, FST is bounded by, again, the same thing, but now we need a margin. So this risk bound. So by the way, this risk bound is tight in some special theoretical cases. So you can come up and fabricate some cases where AdaBoost just follows the worst case. FST. So plus 2 times rho, the Rademacher complexity of n points of Fs plus, and then 1/2n, and 1/n. Okay. So now, yeah. So this is our bound, but here, here we take a linear combination, a convex combination of functions. And so we can assume that sum of coefficients is equal to 1. We can rescale the coefficients. And because here we take the sine function on the end, we apply the sine function in the end. And so we can, so we will rescale them. And so we will say that this function, let's call this g before we take the sine. Like we did before, we say there's a g of x. And so we can say that f of st, sorry, that this should be g. So we can say that g is in as convex combination of the base classifier. And so, and the margin risk bound, and so we need to divide by the margin. In the margin risk bound, we have we take the set of regression function before applying the sine function. And this set of regression function before the sine function, we can assume it's convex combination. So I already said sum is equal to 1. And so we can say that convex of B. And the Rademacher complexity of convex combination of B is equal to B. So after T boosting rounds, we have convex combination of T classifiers. And so I could write in the notes, I've written it with some subscript T. But it doesn't matter. Convex combination of any number of functions from B is bounded by Rademacher complexity of B. Equals Rademacher complexity of convex combinations. So this is our power property. And this explains why the risk bound does not go does go down. But know that there is curious property here. Training error goes to 0, but when we keep boosting, test error keeps going down. So why is it happening? It can be explained by risk bound. So while the boosting continues, the margin becomes bigger. What is the margin? So what, okay, so what are we doing basically? We are fitting, so let's consider the vector given by all the base functions. So I call them F1. So let us think about feature vectors like this. What we are doing is we are fitting a half space on these base vectors. And so we can understand what kind of, and so we can look to the points and we can define a margin. But the margin here is defined slightly different. Because when we train coefficients, we look to convex combination in our risk bound. It means that we normalize coefficient with the 1 norm. For SVM, we are normalizing coefficients with 2 norm. Of W. Here we normalize with 1 norm. It's the only difference. But while we continue training, the distance according to 1 norm between the closest points to the margin can still increase. And this rho, so in other words, we can increase the rho here after we have more boosting rounds. And when rho increases, overfitting error decreases. So it's the opposite behavior. And so let us make a picture. So what is happening in boosting? So here are 2 dimensions. So we have some pluses, minus, 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 minus. And so it can happen that at some point we find some coefficients alpha. So alpha is in Rm. So I just write 2 x's. And alpha separates all the pluses and the minuses. But then how will so what is happening with the weights here? So we have some weights here, and so when we go to the next boosting round, we will look to a base classifier. And now we have special weights. And what typically happens is that the weights close to the border, they are bigger because they were the ones that were last updated. So the plane changes in small steps. The closer you are to the border, the bigger the WT. And so we will select a new function that focuses on these nearby points, very similar to SVM. So we will increase, so now we will select a new line, and it will, so maybe the new classifier will be something like this, because these weights are quite important. And that means that our new hyperplane will be shifted a little bit. And that's how wrongly classified points like push on the plane. But in this classifier, know that this one is misclassified and this one are misclassified. These points now get bigger weight. And so it can happen that, so they become important. And now maybe we will select such a hyperplane So know that by assumption, we don't have lines that are good for all the points. And so AdaBoost will iterate through the points that are closest to the hyperplane. And each time select some of them that are bad and some of them that are good. And these points that are close to the hyperplane, they get bigger weight. And so it will cycle through bad hyperplanes, each time increase the weights on points that are nearby the hyperplane. And it will continue to do so. So in the homework, there is exercise like this, where you have to go through some cycle on 6 points or something. But then you will see that only 3 points are relevant and so on. Okay. And so this is what is happening. So this plane, this is still optimizing the minimal distance of the points because they are iteratively selected. So this is intuitively what's happening. Okay, and then there is a really cool theorem. I will just state the theorem and then finish. Well, actually, sorry, 2 theorems. Yeah. So first, let us remember what is learning assumption. So we said that error goes exponentially down if each HT is better than random guessing by a gamma number, which is positive. Gamma is called the edge. And so the theorem says that if for every set of weights W, we can find a base classifier whose error is smaller than 1/2 minus gamma. So if such base classifier exists, then not only the risk goes to 0 exponentially fast, also the margin risk goes to 0 exponentially fast. And this means that if for all weights W, we have a base classifier with edge gamma, then there exists a classifier whose margin is at least epsilon. And moreover, AdaBoost finds this classifier. So let me write the theorem. Oh. So this is called weak learning hypothesis. So let us fix base classifiers F1 till Fm and the training set S. And then the weak learning hypothesis with X gamma says that for every set of weights W in delta n. So what is delta n is probability vectors with endpoints. So did we use it already, this symbol? But you understand that, so delta n of 0, and then the 1 norm is equal to 1. And for every delta, delta n, right, like this, like minimum and minimum s of probability x I not equal to yi. And here is the theorem. This one. This is the weak learning assumption for gamma. And second, so weak learning assumption for gamma implies that there exists a classifier with margin 2 gamma. So this is kind of stronger than we saw before. So AdaBoost guarantees to find margin for enough boosting rounds, margin for in the limit, infinitely many boosting rounds, find margin gamma, and then there exists a classifier. So there exists alpha in delta M, for which the margin minimum. Now I need to write what is the margin, but it is L1 margin. So alpha 1 F1 I plus alpha M M X I times Y I, and the minimum over N is bigger than 2 gamma. This is the theorem. So these are equivalent. So if weak learning hypothesis holds, then there exists some classifier that has margin 2 gamma. But for AdaBoost, there was the other theorem. I didn't write it down because we're at the end of the lecture. It guarantees to find a margin hypothesis with gamma, but it is kind of like one margin. We normalize here with one norm of gamma, of alpha. And so it's kind of remarkable. So this margin hypothesis seems to be a strong explanation of why AdaBoost does not overfit if you keep boosting for a long time. Eventually it will overfit because margin risk focuses too much on nearby points. So if there is on some data sets with noise, it is bad. But if you have noiseless data set, this algorithm is good. Okay, and so, but there is also a problem. So people say, okay, if the margin is the explanation, why not directly optimize the margin? So this is a linear programming problem. You can write it down and people run solver. And then they say that test error becomes worse. So if you directly optimize, even if there is no noise in the labels or the inputs, there is special data set ionosphere. And if you train the data set with high probability, you will find that direct optimization of margin will find bigger margin for every single input in the training set. It's kind of special data set, but still test error will be bigger. So that means that this margin explanation, it has something wrong. And so people try to investigate this, but never managed to figure out what is happening. So I also gave this task to a student, and also he didn't figure out what was happening. And so just we can look to all of the proofs and look to the inequalities. There are like 4 of them, and then try to understand which inequality is kind of create the discrepancies, the strange discrepancies. And yeah. So there comes just a big mess because there are several inequalities that are quite bad. So where you lose a lot of factor in the test errors. Okay, and then one tried to understand what's happening, but it's very confusing. So maybe people didn't try hard enough to understand what is happening. So yeah, but it's kind of remarkable that AdaBoost finds optimal margin within factor 2. So margin within 1 norm and 2 norm, they differ by square root n. So you can expect big differences, that they're very different objects. But somehow AdaBoost finds with factor 2 from optimal margin after enough boosting rounds. So yes, so partial success for explaining this algorithm. And so hopefully one of you will invent a better reason why it happens, what is wrong with the ionosphere data set, or maybe nothing is wrong, but how can it be explained that such simple algorithm works so well? And margin hypothesis works. Yeah. So it really looks like something about this margin needs to be improved, but not clear what. Okay, that's enough. I was 9 minutes over time. So,
Could you please explain? So, there is a probability of f of xi is equal to yi. So, what is f? It is.
sorry, not the equal, different. So there's the error probability. Weak learning hypothesis for every weight vector. So this should be fs.
Okay.
Yeah. Sorry, just the best base classifier. Yeah, my mistake. Yeah, thank you. Yeah, you should ask directly. Okay, so I will. I have a quiz. I will go into the corridor. Just give me 2 minutes to upload.
По поводу вот она говорит, вот скажи, мы не поняли, она говорит, да, вот это просто не бывает, окончательно работать.
Yeah, you can comment.